Okay, everyone. In this episode, I want to talk to you about how we're going to define union for NAT sets, because your definition for subset is going to be very similar. So one of the really nice things about the sorted representation of NAT sets is we can define a very efficient union. Think back to how union worked on the no duplicates invariant NAT set, our original one. It was a nice version, but it just went through the first set, L1, all the way, looking at and sort of inserting each thing into L2. We can do a little better with the sorted one, where we work through both lists at the same time. But the idea is, well, look, if L1 is sorted and L2 is sorted, you just look at both of the lists and take an element from the one that's less than, right? Choose the lower one. And we can merge the two lists, kind of like zipping up a zipper. Um, That's a great plan. It's an operation typically called merge and is used in another famous sort algorithm called merge sort. That's one of the most efficient sorts that we know of. It's a super useful operation. Here we're just going to call it union because we're using it to implement the union operation, but merge is another great name for it. There's a problem, and maybe you've already noticed it if you've looked at the Emacs buffer here. I got the fail keyword here. This is not going to work. All right, let's see why not. The command has indeed failed. Well, at least we were right that it wasn't going to work. Cannot guess decreasing argument of fix. So shades of that decreasing exercise. What's going wrong here? Well, which of these is decreasing? Is it L1 or is it L2? Well, let's look. Let's look at what the code does and we'll see if we can figure it out. Maybe Cock is just being dumb. Okay, well here, these cases are easy, right? If you run out of one list, then you just have what's left in the other list. You're good to go. Now, if both lists have an element, we'll compare them. And if x1 from L1 is less than L2, well then great, that's the one we'll draw from. So we'll return x1 and then union what's left of L1, L1 prime, with L2, here written out completely. If they're equal, well, there should be no duplicates, so we'll just strip it from both. So we'll do the recursion with L1 prime, and with L2 prime dropping x2 on the floor because they were equal and we shouldn't have two copies of the same thing in the list. And I wrote x1 here, we could have just as easily written x2, like what's the difference? Feels fine. So at this point you might be saying, well, easy, it's L1 is the thing that gets smaller every time, but let's look at this last case. What if comparing these two lists, there's something from L2 is the lower one. So the thing from L1 is greater than the thing from L2. Well, in that case, you want to take the thing from L2 if we're going to sort of zip them up into a sorted list, which means, all right, well, we'll do the recursion with L2 prime, but not L1. So in these two cases, we're decreasing in L1, but in this case, we're decreasing in L2. Now, you'll notice there's some other properties that let us know as humans that this is a good definition. We're never increasing, right? In the cases where we don't decrease, we stay the same. So something always shrinks on a recursive call. So really, if you like, you could say, well, look, if we took L1 and L2 together, if you thought of them as a pair of like a single long list appended together, or as we're decreasing in the total length, right? Some element gets used up. At least one gets used up in every recursive call here. Here we use one. Here we use one. Here we actually use two because both x1 and x2 are sort of used up in some sense. That to me constitutes an argument of why this function should terminate, but it's a slightly too complicated argument for Coq to really get it. So what a letdown. How are we going to be able to write this function? It turns out there's a really nice trick. Let's see what it is. So there's some discussion of what's going on. I'm just going to show you the trick. So the trick is to define an inner recursive function where the inner function is decreasing in the second argument and the outer function will be decreasing in the first. So what I've done here is I've said, well, look, the body of my function is this inner loop, and I'm just going to start the inner loop on L2. Now there's two kinds of recursive calls I can make. When L1 decreases, remember these first two cases, I'm going to call the outer function union, right? And so union will be decreasing in its first argument. When only L2 decreases, I'm going to call inner. And you'll notice inner takes only one argument because it's closed over that L1. We've seen this notion of closure before in my n to 0 implementation, right? The one that did the subtraction. We saw that in class and posted on Zulip. So This trick basically says, look, if I need to make two different kinds of recursive calls where it's decreasing in one mode or decreasing in another, I can do this inner loop to do it. Okay, so if you like, we can kind of play around with this a bit. Let's see how this works. Compute union, and now let's do 1, 3, 5, 7, 9, 0, 2, 4, 6, 8. Beautiful. So it certainly works, right? It's zipping them up. What's really happening? Let's look at a shorter example. Okay, let's see what's really going on here. So let's get the code up here on the right, and let's just walk through what's really happening. So what's going on here? Here, let me. A little too big. There we go. Perfect. Okay, let's really see what's happening here. So union 1, 3. Which case are we going to be in? Well, we'll be here. This will be 1. This will be the list just 3. This will be 0. This will be the list just 2. Okay, so we're in this case. So that's going to be equal to inner, so it'll be, 0 cons inner, just the list 2, where, and then now when we're going here, what's it going to be? Well, if we're doing the inner loop here, we'll have left L1 alone. So L1 will be equal to this. Okay, so what's going to happen? We'll again just be an inner with the same L1. L1 hasn't changed. So we'll get inner. So what's going to happen there? So then we'll be in what case? So L1 will be the same thing, 1, 3. L2 will be just the list 2. So then we'll be in this case again, where X1 is going to be 1 again. L1 prime is going to be the list just 3. X2 is going to be 2. L2 prime is going to be nil. So now we're going to be in this case. 1, cons, and now it's union, just the list 3, just the list 2. Okay, what happens after that? Well, we'll be at 3, 2, we'll be here. This will be 3, this will be nil, this will be 2, this will be nil. We're in this case again. Excuse me, so it'll be 2 cons. Right, so notice how the fact that inner has closed over that L1 is the key thing for this recursive call working, right? It's sort of remembering the value of L1 without us even having to pass it as a parameter. Okay, so then what happens? So we're there, so we're at 0, 1, 2. And so what'll happen? Okay, so now we'll be in the case where L2 is empty. This is just the list 3. So we'll get this, which is 0, 1, 2, 3, which is exactly what we were looking for. Hopefully that clears it up. All that's happening is substitution. The trickiest bit here is this remembering the value of L1 that's happening for inner because it's a closure. It's closed over that value. If you're stuck about that, I think trying to do one of these evaluations yourself will be super useful. If that doesn't do it for you, as usual, I think the goal is to take it to Zulip. Okay, let's just pop back up real quick. What are you going to have to do? So in subset, you're going to want to write subset for these sorted list NAT sets. And to make it efficient, you should walk through both lists at once, following the pattern of union. Now that might seem tricky at first. What do you do? So my advice would be, look, when I say following the pattern of union, you can copy this code, and what needs to change is, well, okay, look, you have to return something different in each of these cases that I'm highlighting, but the rest of that structure can stay the same. Okay, a little bit of careful thought around the compare will also do you well. Once you've thought about these and you've done it, I want you to do this quiz. So if you haven't yet tried or successfully written subset, Don't watch this last part of the video for the quiz. It won't necessarily make sense. It won't hurt you, but once you've done it, come back and let's do the quiz. Welcome back. It's great to have you. So, if we were going to write set equal for sorted list subsets, would you reuse subset like you might have done or ought to have done for set equal up above in the original invariant? Or would you define a new recursive function and why? Okay, so I think there are two different answers here. So reusing the subset is nice because it's simple, but you could write really efficient code to test for equality here. What's nice about the sorting invariant is that for a given set, there's only one representation. So you could check equality by just walking down both lists recursively in a single go. And just saying like, hey, these have to be exactly the same in every position, or one of the sets has something the other set doesn't have. Um, okay, great. Hopefully that makes sense. If it doesn't, try to formulate a question on Zulip, but maybe play with it first. If you're really unsure, try writing the function. It's not for credit, but you'll certainly learn something if you do it. Okay, there's one more video coming at you after this where I'm going to talk about a final representation for sets where we use binary search trees. And that'll be it for the day. Hope y'all are doing well. Cheers.